table. Okay. That's it. Turn around to your right, be better. I don't want to go into the sun if I can avoid it.
In the 1960s, we thought we will have colonies on Mars by the year 2000. We had the rocket, the maths, and the ambition. What we underestimate here was the system needed to survive there. Today, we are making the same mistake with humanoid robots. We are building large models, but we are missing what makes them survive reality. In 2010, robots were doing backflip. 15 years later, there's still no humanoid in your home. And it's not a hardware problem or lack of compute power. It's a system problem. Recently, a new race has begun. A race to build general-purpose humanoid robots. Companies promise machines that can work beside us, adapt to your home, and learn new tasks on the fly. Billions are being invested. Demo looks increasingly impressive. But impressive is not the same as deployable. And progress in the lab is not the same as survival in the real world. So the question isn't, are robots improving? Of course they are. It's just that between a humanoid robots and a robotic arm, there is a huge complexity gap between how you control them. And so for most of modern robotics, we choose the easier routes. Specialized machine, fixed base, structured environments. Factories around the world run on robotics arm. They sort, they assemble, they repeat the same motion millions of times. However, humanoid research never disappeared, but it remained conscious, incremental, and aware of the physical constraint. For decades, humanoid robots remained a dream for scientists. Then, something changed.
Transformers. Like large transformer models?
A transformer language model.
Transformers are not this one, Lily. This one. That's the backbone of the AI revolution since 2017. If you don't understand the math, it's totally fine. What matters is that it allows a model to weight relationships between elements, words, pixels, or even actions. It made models dramatically better at interpolation, giving them enough data and they can generalize surprisingly well. And what is the most abundant resource on the engine? It's text, trillions of sentences. That's why models like ChatGPT improve so fast. But here's the difference. If it hallucinates, it's a funny screenshot. But if a humanoid hallucinates while holding a child or working near a glass table, it's a lawsuit. Language models operate in static data. A humanoid robot operates inside physics. Every action changes the state of the world, and that difference changes everything. Training a humanoid is nothing like training ChatGPT. A language model needs text. A robot needs vision, language, and motor control all are linear in time. We call this system Vision Language Action Model, and their data is brutally expensive. Each example isn't a sentence. It's a stream of sensor reading, motor command captured from real-world interaction. Training usually follows two phases. First, imitation learning, the robot watch human demonstration and learn to mimic them. But data collection is really time-consuming. In addition, watching someone clean a table is not the same as cleaning one yourself. So we add reinforcement learning. Let the robot try, score the attempt, and repeat. We use simulation, millions of virtual trials, thousands of lifetime compressed into silicon. And yet, something is still missing. During training, tasks are segmented. Clean the table, the robot executes, the episode resets, and the world goes back to its ideal configuration. But real life does not reset, action leaves trace. Each diversion is tiny, but over dozens of instructions, the system drifts, not because the initial state was random, but because the robot is operating in a world modified by its own imperfect action. It was trained on expert trajectory, but real life is a trajectory generated by the robot itself. And that difference is fundamental. Furthermore, the model clonage is static. It encodes only patterns from training data, but it does not build an explicit, updatable model of your environment. If the world changes, it does not reason about the change, it interpolates. That is not the same as adapting. Humans accumulate context. We remember what we moved 5 minutes ago. We update our internal model continuously. So, the robot faces two structural limits. It cannot update its internal model of the world, and it cannot robustly recover from its own long horizon tree. Those are not hardware problems, they are architectural problems. And the dominant answer today is simple: scale. More data, bigger model, more compute. If scaling worked for language, why wouldn't it work for robotics? But autonomy does not emerge from scale alone, it emerges from structure. We didn't reach the moon by building a bigger engine. We build navigation, redundancy, planning and verification. We build a system. And today, many approaches try to unify perception, reasoning, memory and control inside a single large foundational model. It's an appealing idea. If one model can understand everything, why not let it decide everything? And for short demonstration, it worked surprisingly well. But autonomy is not a demonstration. If you cannot diagnose failure, you cannot deploy safely. And in robotics, safety is not optional. Scaling increases capability, but autonomy requires structure. So where does that leave us? We have seen 3 structural constraints. First, embodied data. Training in simulation or controlled environment is not enough. However, collecting enough real robotics data is really hard to scale and really costly. Second, compounding error. In the physical world, small deviations accumulate over time. When deployed, in fact, robustness becomes more important than raw performance. Third, static knowledge. Today's models don't really evolve with experience. They are in fact good to generalize within their home distribution, but not really to adapt to something unseen. And none of this problem really disappear with scaling alone. What seems necessary is structure. A system that can combine reliability with classical robotics, for example, instead of just replacing it. Something that are designed to recover, to adapt really to its environment. This raises a deeper question. What would look like an architecture if we design it from the beginning for real-world deployment and not just for raw performance on benchmark? And that's the question I'm trying to answer during my PhD at CNRS. Not at a final answer, but more as a step towards something more reliable. Because I'm convinced if humanoids are going to work, it won't be by scaling alone. It will be about design. So stay curious and see you in the next video.